Thank you, everyone. Thank you, everyone, so much for coming. So I work at 47 Degrees, soon to be Xebia functional. And like my colleague Bako said, we do a lot of functional programming. And the KotlinX Flow data type is actually a little bit of functional programming in disguise. So it's many things in Kotlin. So today I want to talk a little bit about functional patterns that we use with streaming and see how we can apply or reason about them in Kotlin. So first I was going to briefly introduce myself. So some of you might know me from my personal work on GitHub or my work on Arrow. There's also my LinkedIn and my Mastodon account. I'm not promoting my Twitter anymore. And what do I want to talk about today? So when we do functional streaming, we typically work with pool-based data types. And I also want to talk a little bit about reasoning about pool-based data type and reasoning about KotlinX Flow, how we can use these techniques to stream resources, and a little bit about how we can apply these techniques to parallel processing. So first I want to establish a little bit of terminology. So when we are talking about streaming, we often talk about an upstream. You can imagine an upstream as a tub of circles, right? So there's an upstream data source producing elements, in this case, circles. And then we typically have a pipeline that takes these elements from the upstream and applies a function to it. So in this case, we are turning the circles into squares. And that results in a downstream. So we get a new stream, downstream with squares. And when we are transforming circles into squares, it can typically take some time. Imagine that we're doing some graphical processing or we need to communicate with the database. These things take time, and our tub of circles is filling very, very quickly with elements. So if we do not do anything about this, then eventually the tuple overflow with elements, or more practically put, our memory will fill with elements, with values, and eventually our memory will run out. So we need a way of the downstream to communicate to the upstream how fast we can process these elements. That is what we call backpressure. And this is probably one of the most complex things that we have to deal with when we are streaming data. So what does this look like in the context of pool-based streaming or in the context of KotlinX Flow? So in KotlinX Flow, we have the flow collector interface, and this is what everything is about when we work with the KotlinX Flow data type. And there's only a single function in this interface. So that's pretty neat. There's not a lot that we need to learn to work with KotlinX Flow. There's this emit function that sends elements or circles downstream. And if you notice, what is most interesting about this function is that the function is suspending. So in Kotlin, I'm sure we all love KotlinX Coroutines. We love Kotlin Coroutines. We love suspend. What is actually happening here, if you send a circle downstream, this function will not return until the downstream has processed this element. So we get this automatic way of communicating from the downstream to the upstream how fast we can process these elements through the Kotlin suspend system. So what does this look like in practice? So imagine we have a class that represents our circle, and the circle keeps count of how many elements are going downstream. And we have a function, produce circles, that is emitting or sending elements or circles downstream in the flow. So here, and this might look a little bit foreign to a lot of Kotlin developers, I've put the flow collector interface in the extension of the function, so that in the function body, we have access to the emit function. And then we create a counter so that we can keep state. And in this case, we can safely use a var, because we know that this producer of producing of the circles is single-threaded, so there's no concurrency happening. So we are fine using a simple var value. And the second thing that might look foreign is the while-true loop. So typically, when we're doing programming, we don't often use while-true loops. But in KotlinX Flow, it is completely safe, because KotlinX Flow can, through the emit function, also control whenever the while-true loop stops. So here we can very simply model a function that infinitely produces circles. And downstream, we can control how many circles we want, as you will see in a little bit, or at what pace that the circles get created. And first, we create a circle incrementing the counter. We make a simple log statement, and we emit the circle downstream. And if you want to turn that into an actual KotlinX Flow value, we can very simply call this function inside of the flow builder, and that gives us a value of circles. This might look a little bit more common, right? So most common is that we write this function body that we saw before directly into the KotlinX Flow builder, and then our code will look a little bit like this. So this is typically what we'll find in a Kotlin code base. And then we have our pipeline, so the function that transforms our upstream of circles into the downstream of squares. And here I've created a square class that has a private constructor, because I don't want, or it's not possible for anybody to arbitrarily create the squares. So in the companion object, I create a suspend function that takes the circles and turns them into squares. And as you can see here, it takes 1 second to convert the circle into a square. So like I said, I'm here simulating or emulating that we're doing some graphical processing. So it takes some time to turn the circle into a square. So if you can imagine, the infinite while true loop creating the circles is much, much faster than this conversion or transformation from circle to squares. And again, we have a couple of simple log statements to see what is going on. And if we put all of these pieces together, we have the flow that is emitting the circles, and we say take 3, right? And this take 3 makes sure that this while true loop that we saw before is limited to only creating 3 circles. And we then collect the circles from it, and we call our toSquare function. And if you remember from before, I mentioned that our emit function was suspending, and it did not return before the downstream finishes its function. So here, only the next circle will be created when the toSquare function finishes. And we can also see that in the output of the program. So first we create the circle, then we create a square. We say we finished creating the square, and only then would the next iteration in the while true loop happen, creating another circle. So how can we visualize this to see what is actually going on in code or in the runtime? We can represent our circle function, or the creation of a circle, with a purple arrow. And here, I'm only interested in the piece in the while true loop, because this is actually the only function that's actually creating the circles. All the other stuff around it, like the var counter, we can consider it outer state, right? The while true loop is just the way of modeling that we are creating an infinite amount of circles. And our downstream, or our pipeline, is simply our function taking the circles and turning them into squares. So here we present this toSquare function with another arrow. And then we can visualize our program like this. So we have our while true loop with the purple arrow creating the circle, and our second arrow creating the square. But we were not looping forever. Instead, we were looping the first time with an index of 0, second time with an index of 1, and the third time with an index of 2. And this was the entirety of our main function that we just saw. And what is interesting here, if we visualize this, is Kotlin optimizes this program in such a way that it sequences the functions that we saw, or the arrows that we saw in the different functions. It sequences them in this sequential way automatically in the compiler. So the Kotlin compiler does a lot of very powerful things to make sure that all of these different codes get sequenced and they run in a single coroutine. So this is really, really efficient. This is really, really optimized thanks to the Kotlin compiler. And it's a technique that I've not seen in any other language. So this is techniques that we apply in functional programming as well. But typically, it requires a lot of elaborate machinery that we need to write at runtime. It's very heavy on the runtime. The Kotlin compiler takes care of this all for us. It's very efficient and very fast. So how can we apply that reasoning of automatic back pressure to different things like streaming resources. Imagine that we need to read all the lines from a file on the operating system. So from a given path, we need to read all the lines into a KotlinX Flow. Oh. So luckily, Kotlin standard library offers a lot of very great tools. So for example, the useLines function is a function that comes from the Kotlin standard library, and it reads all the lines of the file into a buffered reader, right? So in a streaming manner, it will create a buffered reader and read all the lines from the file one by one. But if you remember working with Java buffered readers, and we don't have to do that a lot in Kotlin thanks to these amazing tools, but it's important that we open the buffered reader, and then when we're finished with reading all the content from the files, that we close it again. And this is important because operating systems have a limited amount of file handles to work with. So it's very important that once we finish the work, that we close the buffered reader so that the operating system can free its resources to other programs that we are running on the machine so that it can work as efficiently as it can. And what is happening here in the useLine function is that it gives us a sequence of strings, so a sequence of the lines in the file. And here you might already be wondering, well, if we already have this lazy sequence of lines, why do we still need KotlinX Flow? And we will see that in a second. But what is interesting here is, again, this emit function. So we loop over all the lines in the sequence, and we emit them downstream. But because we have this automatic way of back pressure that we just saw, that will make sure that only after we looped over every line in the sequence, we emitted it downstream, we processed it downstream, the buffered reader will stay open because this emit function will not return before the downstream have finished behavior in the KotlinX Flow, that our buffered reader stays open for as long as downstream or in the pipeline we are processing the lines from the file. So we don't have to do a lot of work. We don't have to keep logs, or we don't have to do anything special. We get this behavior for free. So imagine, like I said, typically when we're writing backend applications or front-end applications, we have to do more than simple things. So for example, we need to upload every line from the file to some blob storage in the cloud. We typically want to use suspend for this. So Kotlin sequence is not sufficient because Kotlin sequence is also a lazy stream, but it does not support side effects or suspension that we might need to upload things to the cloud. So a lot of us are typically using Kotlin on the JVM, and here I have a simple pseudo example. Imagine you are working with GCP or Azure or AWS, and you're relying on the Java SDK. You might encounter a class like this. So we have a SDK client for uploading files to the cloud storage, but it returns us a completable feature, right? Luckily, KotlinX Coroutines offers us very simple ways of converting the completable feature into a suspend function, so we don't have to do any heavy lifting. We can just call the await function, and we can turn the completable feature into a suspend function without writing a lot of boilerplate code. And we here do it very conveniently by creating an extension function on the Java SDK, exposing a suspend function over the existing completable feature. Now, if you put all of these pieces back together, we create the Java SDK. And again, we have this use function that we saw before with useLines, and opens the, maybe important to mention, the Java SDK, typically, as you will also see a lot in Java SDKs, it implements auto-closable. So when we construct the blob storage or the Java SDK client, we at some point later in time have to call the close method, right? So in Kotlin, we have the use extension function for auto-closable or closable. So we can create our Java SDK client and use the storage or the blob storage client. And then inside we can say, okay, I'm going to create a path pointing to the path on the file system. I'm going to read all the lines from the KotlinX Flow, and then I'm going to collect every line lazily in a streaming way from the path system and upload them one by one to the cloud storage. So this is quite interesting, but we are returning unit. So we are losing all the results from uploading our files to to the cloud. So potentially we want to later inspect what happened to every line that we uploaded to the cloud. So we would actually prefer to get another result of the flow data type with all the individual results as we uploaded them to the cloud. And to do so, we can apply a similar technique that we did for reading the lines from the path. And we're again going to rely on the automatic backpressure that we get from KotlinX Flow. But this time, we're going to create a single element flow. And this kind of goes to what we typically know about streaming in KotlinX Flow, because if you have a single element stream, you would normally use a suspend function. But what we are interested in here is we want to keep the Java SDK open for as long as we are processing or uploading files to the Java SDK or the cloud. So we're again relying on the automatic backpressure from the emit function to keep the Java SDK open for as long as we're using it downstream. So we create a blob storage, we call the use function, and then we emit it downstream. And this emit function will keep or prevent the use function from calling close until we're completely finished using it downstream. And then we can rewrite our previous example like this. So we say we create the single element flow of blob storage, and we want to concatenate it with reading all the lines from the path and uploading all the lines to the blob storage. So our blob storage or a single element flow will remain open until everything that is nested in the concat function is finished running. So only when we've uploaded all the lines to the blob storage, then will the Java SDK or the blob storage flow call the close method on it. Right? So we are able to convert this semantics from autoclosable to flow thanks to this automatic backpressure that we have in the KotlinX Flow data type. And now we see that we have flow with upload results in the return type. So at any later point, we can still inspect all the results from uploading every independent line to the cloud storage. So oftentimes, when we're doing things like this, imagine we have many files on the file system that we need to upload to the cloud. So we want to somehow parallelize this work because we have very powerful machines. We don't want to do things sequentially one by one because it takes too much time. We want to parallelize things, but we've seen that KotlinX Flow sequences these functions, so there's no parallelism going on whatsoever. So we need to fix this. Things are running in a single coroutine, but we want actual things to happen in parallel. So what does KotlinX offer us to do, or what is a common technique in functional programming to solve this problem? We create a coroutine that is reading all the lines from the path. Imagine here we are reading 3 lines from the path. We then want to upload 3 lines in parallel to the cloud. But as you can see here, we seem to lose this automatic backpressure that we've been talking about, because we are not simply sequencing functions anymore. We now have 2 separate coroutines, so this mechanism seems to break. That is actually not the case. So what KotlinX offers us, or what is very common in functional programming, is we put a channel or a queue in between. A channel is a type that comes from the KotlinX Coroutines library. It's like a queue. In this case, we create a queue or a channel with 3 elements. And these channels and queues in Kotlin also automatically, or out of the box, support suspension. So what happens is we read 3 lines from the file system, we put them into the channel, and our downstream coroutine uses this suspension mechanism to keep this automatic backpressure guarantee intact. Right? And KotlinX Coroutines offers us a very optimized way of doing this. So Kotlin is really, really great at optimizing all these things and providing its very efficient implementations. So typically in Kotlin, we don't have to do this ourselves. There's a builder for this that does this all out of the box for us. But the important thing to remember is that even if we want to do parallel processing, this guarantee of automatic backpressure stays intact. So let's take a quick look at what that can look like. So I was talking about uploading 3 lines in parallel to the cloud. And here I have a function parmap unordered, which comes from the ArrowFX coroutines library. And it's very simply, we changed map to parmap unordered, and we say capacity or concurrency 3, and this way you can upload 3 lines in parallel to the cloud. The unordered word here is quite important to remember, because if we are doing parallel processing, to do it in the most efficient way, we will typically interleave elements, and that means that we lose the original order of the elements. And I will very briefly here show the implementation from RFX Coroutines. So the flatten merge comes from the KotlinX Coroutines library, and basically what that does is it takes 2 nested flows, so 2 nested streams, and it will interleave them as efficiently as it can. And because of that, we will lose the order of the elements. So I map the original stream, taking every line from the file, and I create a new flow, and I say, in this new flow, single element flow, I'm going to apply my transformation or my function to upload things to the cloud, and then I'm going to merge them in a parallel way. And because of that, we lose the order. But in this case, we might not want to lose the order, because we are uploading lines from the file system, and maybe the order of the lines is important, because if we later on expect the results, we might want to know what was the original order that we processed them. So RFX Coroutines also offers a parmap function alongside parmap unordered. And this function will actually guarantee that the original order is maintained. So the flow that we now have in our return type with the upload results will have the same order as the lines that we found them in the actual files. And to give you a very brief idea of how this works is it creates completable deferreds or promises in the same order as the original flow. It then runs everything in parallel and completes the promises in the same order as we process them. So for a penalty of 1 completable deferred per element, we can now guarantee that the order is maintained. So it's a small price to pay if and only if it is required that you maintain the order of the elements in the stream. So to draw a final conclusion, KotlinX Flow gives us a very efficient and strong way to reason about composable streaming in patterns that you might be familiar with from functional programming, some of the things that I talked about here. But it's the most critical thing here is that we get automatic back pressure thanks to this very efficient implementation by Kotlin Coroutines in the suspend system. And of course, my favorite, we have suspend everywhere, so we can run side effects. We can very easily read things from the file system in efficient ways. We can upload things to the cloud, get all these powerful tools that we are normally using in our day-to-day lives, also available in this very efficient streaming data type. Thank you so much for your attention. Do we still have any time for questions?